Hello, everyone. My name is Janak, and I'm the product manager for Amazon Athena. And I'll be joined for this talk by my co-presenter, Anthony, who's a principal engineer on my team. And I know that I speak for the both of us when I say that we're absolutely delighted to be here today to talk with all of you about Athena. How we think about Athena, explain a bit about where we see Athena's future, and introduce some of the work that we've done over the last 1 year to help realize that future. So by way of a quick show of hands, can I get a sense of how many of you here use Athena regularly? Pretty fantastic. Thank you for being Athena users. But for those of you who have not yet used, I'll do a quick intro. So Athena is a very powerful query service that allows you to submit SQL statements to make sense of your structured and unstructured data. Out of the box, we are integrated with AWS Glue for metadata management, and we support querying data that sits in Amazon S3. So Athena is also serverless, so when you submit your queries to us, you don't have to manage your servers. We do all of that heavy lifting for you. So that is what Athena is today, and we've received a lot of feedback that this is not where you want Athena to be in the future. So some of the future items that we want to consider are, you've told us you want to use Athena for ETL use cases. We want to support that. You want to use Athena to query any data source and not just data that sits in S3. We want to enable that. You want to use Athena for ML use cases. We want to be right there to help you to run your inference. So that is what we expect Athena's future to be. Here are some of the breakout sessions, but I think some of these might have taken place already. We do have a workshop later in the day, so we hope to see you there. And this is how we're going to be spending our time today. So we're going to go over some common Athena usage patterns. We're going to understand the key personas that exist in an organization, and we're going to dissect and understand their use cases and challenges. I will then introduce some of the new work that we've done over the last 12 months to help solve these challenges. And then Anthony will take the time to walk us through a demo, which I know you will find as exciting as I did when I first saw it. So without much further ado, let me start by showing you some of the most common Athena usage patterns. So a lot of customers use Athena for ad hoc investigations. In this example, you can see that the customer has data in various data sources. They have data in Redshift, they have data in Amazon RDS and DynamoDB and in a lot of other places. They run ETL jobs, and the data is ingested into Amazon S3. They then populate the metadata in Glue catalog, and then analysts in this organization use Athena queries to do ad hoc investigations. At times, they also use to connect to Athena, a BI tool, and that they do by using our JDBC and ODBC drivers. Customers are also increasingly using Athena for SaaS use cases. So in this particular example, you can see that the customer has hot data in a relational store like Amazon Aurora, and they have warm and cold data in S3. Now, when their external customer request comes in, it goes to the API gateway, and the API there joins the data which exists in Aurora with data in S3 via an Athena query. We also support, and a lot of customers use us to do ETL and then subsequent query analysis. And that is easier because customers already have their service logs sitting in Amazon S3. They then dump their application logs and then the logs or the data that they source from their external partners into raw formats in Amazon S3. They then use Athena's create table as select statements and insert into statements to update the metadata and the partitions in the Glue catalog, and at the same time optimize and store the data in the final location in S3 in a format such as Apache Parquet, which could be optimized for analytics. And then analysts in this particular organization again use Athena queries to do their investigations. So these three are not the full exhaustive list of the use cases for Athena. These are just some of the most common use cases and the information that I've learned from most of you here. I just wanted to relay it back to the community for the benefit of all. So let's switch gears for a little bit and understand who the key personas are in the organization. So for the purposes of this presentation, let us take the example of a fake e-commerce company. Now, this e-commerce company has been around for a while, and over time, their technology stack has evolved, and teams in this organization use the data source which is the best fit for the application that they're building. So for instance, when the user request first comes in, they're shown a product catalog, and that product catalog is stored in Amazon Aurora, which is a relational data source. They have a payments service that uses HPAs running on EMR. They also have an order processing service, which processes active orders. And active orders are defined as orders which are submitted by the customers, but not yet fulfilled by our e-commerce company. And they have to be frequently rendered back to the application. And to enable that, they use Redis. Their customer-specific information, such as email address and shipping address and phone number and all of that info is stored in DocumentDB. Infrastructure logs are stored in CloudWatch logs and CloudWatch metrics, and these are used to debug any and all issues that may happen. Now, our e-commerce company also has a business intelligence and a data analyst team, and that team uses Amazon Redshift for long-term and historical analysis. And finally, they also have a shipment tracking service that relies on DynamoDB. So who are the key personas in our e-commerce company? We have Anna, the analyst, Carlos, the administrator, Richard, the engineer, and Maria, the scientist. Now, some of the key use cases of all of these personas are listed here. So Anna, she runs SQL queries. She schedules reports to generate the key performance metrics of the organization and also populates business dashboards. Additionally, she also has to do a lot of ad hoc investigations. So for example, let's assume that customers of our e-commerce company are complaining that their orders are stuck in a weird state. Then Anna would be tasked with aggregating the info from all of these various data sources in near real time and identify what specific orders were stuck. Carlos, he has the non-trivial task of creating, maintaining, and managing the data lake. He also has to specify access control policies for any and all users and roles that exist in the organization. We have Richard, and I personally identify the most with Richard because I used to be him in a previous life. Richard builds stuff. So he builds SaaS applications using Athena APIs, and he also helps Carlos by building ingestion pipelines, and Maria by building applications that can be used to running machine learning inference. And then Maria, our scientist, her primary focus is to build and train the most accurate ML model possible. She also helps analysts and other users in the organization to run machine learning inference. Now, some of the main challenges that these personas face are that Anna, data is spread across all of these various sources, and in order to identify and isolate all of the customers and orders that were stuck, she has to first rely on the data engineering team to complete all of their ingestion in real time before she can run her analysis. Carlos, again, he has to struggle because data is stored in a variety of applications. He has to build and maintain and also scale ingestion pipelines and workflows required to get all of that data from all of these sources into a central data lake. And additionally, teams are going to continue to want to experiment. So in case there's a new team which wants to experiment with a new technology, Carlos has to find a way to support that. Richard, our engineer, also has to support multiple formats. He has to learn how to access and retrieve data from multiple data sources and has to do it all over again in case a new data source is now used by the organization. And Maria, in order to train her ML model, she requires to extract data from all of these sources. And that also as fast as possible, because otherwise her model might be accurate, but for like a month prior and not for the here and the now. And analysts in the organization also rely on her for running inference, so she could be a bottleneck in the organization to run inference. So the next question is like, we know there's all these challenges, but how do we solve for them? So I'll introduce some of the features that we've done that help to solve these challenges. And the first one that I want to introduce to you is federated queries in Athena. So what is a federated query? A federated query is a query that you can write in SQL that can scan data from data sources which could be relational or non-relational, or your object stores, or even your own custom data sources. Regardless of whether you have your data source on the cloud or you host it on-prem, the federated query would be able to scan data from across both of them. And you can use this federated query in complex ETL pipelines for ad hoc investigations and also in your applications. So why do you need a federated query? And it is because of this picture. Now, for those of you with eagle eyes, you might have noticed that in this particular picture, we have an additional data, which is advertising data. Now, our e-commerce company could have stored this advertising data on an entirely new data source. So the point is, architecture is going to continue to evolve. Engineering teams are going to continue to use data sources that they see fit for their purpose. And aggregating all of this data in a central repository is going to continue to be a challenge. And that is why you need a federated query. So here are the key concepts that you need to know about a federated query. So when you submit your federated query to Athena, Athena first has to connect to a data source. That data source we refer to as a federated data source. Now, to connect to the federated data source, Athena uses this new construct called a data source connector. These data source connectors are basically connector code that run in AWS Lambda as functions in your account. So when you submit a federated query to Athena, we would invoke, or we have the ability to invoke multiple Lambda functions in order to optimize for performance when we connect to your federated data source to fulfill the results in the most performant manner possible. So is a federated query simple to use? I think it is extremely simple to use. There's 3 main steps to follow. The first is to deploy the data source connector. The second is to register the data source connector. And when you register your connector, you can specify a friendly name which we call as catalog name. And you can use this catalog name to refer to your federated data source in your queries. And the third is obviously just start writing your SQL queries, and to reference to a table that exists in your federated data source, simply use the 3-part identifier syntax, which is catalog name dot your database dot your table. And finally, we hope that you're amazed and you rejoice when you see the results of your federated query in a very performant manner. So how do you deploy a data source connector? By now, we know that data source connector are Lambda functions, and there's 2 main ways, or 2 easy ways to deploy the data source connector. The first is using one-click deploy mechanism using a service called, an AWS service called Serverless Application Repository. So this picture here shows we've uploaded a connector that we've also open sourced called Athena CloudWatch Metrics Connector to Serverless Application Repository. Users can simply browse to this location, fill in a couple of parameters, hit deploy, and they're good to go. The second way is you can use any mechanism that you see fit. It could be Lambda's UI, Lambda's APIs, or any other mechanism to upload the code manually to AWS Lambda. So this particular picture shows Anthony and I, we've uploaded a couple of connectors to Lambda using Lambda APIs or Lambda UI. And again, as soon as you deploy, you're good to go. Registration of a connector is also extremely easy. Simply fire up the Athena console, hit connect new sources, and you'll see a list of connectors that are available for you to use. In the next screen, hit or fill in a couple of parameters, including the catalog name, and then you just start writing your query. Additionally, we also support a construct called a registration-less federated query. We think this will be extremely useful for you to prototype before you register a connector with Athena for good and enable all of your users in the organization to use that connector. So to use the registration-less mechanism, simply add the prefix lambda : the function name, and this is the function name that you use when you deploy your connector, as the catalog name. So for instance, in the query select star from lambda : CMDB, you're telling Athena to run a federated query using this function called CMDB. So here's a list of the data source connectors that AWS has open sourced. We've open sourced connectors to HBase, DocumentDB, DynamoDB. We've written a JDBC connector that you can use to connect to data sources such as Aurora and Redshift. We've also released connectors to Redis, CloudWatch Logs, CloudWatch Metrics, among others. So what do you do when you want to federate into a data source that does not yet exist in this list? For that purpose, we've also released a query federation SDK that you can use to write your own connector to federate into your data source. Some of the features of our SDK are listed here, and I'll run through them quickly. So we support S3 spill. This is useful in cases when the response of your request exceeds the capacity of the Lambda, and you're then able to spill to disk easily to fulfill your request. We support partition pruning to be able to scan only the relevant bits of information that your query requires and not to increase your scan size. We also have the ability to invoke multiple Lambda functions in parallel in order to optimize for performance of your query. Additionally, we support your request and response types into Apache arrow types. This also helps to improve the performance of your query. We provide to you the identity of the user or the entity that has submitted the query and allow you to hook in the authorization models that you want to help for authorization protocols. We also respect the fact that you could be running analytics or a federated query against a data source that you use live in production, or against a federated data source that is not as scalable as Athena is. And for that matter, we allow you to do or specify congestion control mechanisms. So this is how a self-service ETL job could look like using a federated query. So you can write one SQL query to get data from multiple data sources, and Athena writes all of the query results in Amazon S3. So you get your data into S3 by this time. And you can wrap this federated query around a create table as select or an insert into statement. So what this does is this helps you to create the right partitions in the glue catalog, and you can also specify the format of the data that you want to store in S3 as. And finally, to do this repeatedly or a regular workflow, you can schedule this mechanism or schedule this workflow using a mechanism such as Lambda, or you can build your own scheduling application. The next feature I want to introduce to you is our support for the Hive Metastore. So a lot of customers complained to us, or rather gave feedback to us, that they want to use Athena because of the simplicity, but they are unable to do so simply because Athena only supports the glue catalog for metadata management. This feature removes that limitation. So you can now use a data source connector to connect Athena to any metadata management engine. Out of the box, we've provided a reference implementation for the Apache Hive catalog. And when you use this connector with Athena, you can run a query that in one query scans data from data that is referenced in the Hive catalog with data that is referenced in the glue catalog with data that is referenced in any federated data source. So this picture shows you how easy it is to use our reference implementation to connect to the Hive catalog. Simply fire up the Athena console, hit connect data source, select the right options, fill in a couple parameters, and you're good to go. So to bring it all together, how does federated query help our personas? So Anna, our analyst, is now able to select data from any data source for her analysis. She's able to create a real-time data-driven narrative and identify which exact or which specific customers were affected and what orders were the ones that were stuck. Carlos, the administrator, can deprecate the old ingestion pipelines and move to a serverless ingestion pipeline using just a couple of SQL queries. Richard, our engineer, does not need to learn different data access paradigms. He can use SQL queries to source data from any particular data source. He also does not need to help Carlos anymore to scale and build ingestion pipelines. And Maria, our scientist, she can use data from any data source to train her model, and that helps her to improve the accuracy of her models. The next feature I want to introduce to you is user-defined functions support in Athena, or UDFs. So what are the challenges without UDFs? At times, our personas such as, it could be Anna, it could be Richard or Maria, they might need to pre or post process data before ingestion or before using in their analysis. And that is really difficult to achieve in SQL queries without UDFs. To achieve this, they have to schedule or work with and switch between multiple different applications, which is frankly not the ideal experience. Carlos also has to sometimes provide restricted access to Anna. So for example, he might need to redact sensitive information, which could be an entire column from Anna. And without UDFs, what Carlos does is he duplicates the original data set minus the sensitive information in the form of a column that needs to be redacted, and then provides access to Anna, which is again not the most ideal solution in the world. So with this feature, you can now invoke your own functions in Athena. UDFs are powered by AWS Lambda, and you can use the same Query Federation SDK to author and define your UDFs. Since they are used or powered by Lambda, we also support network calls in these UDFs. You can invoke UDFs in either the select phase and or the filter phase of your query, and you can invoke as many UDFs as you want. And Athena automatically optimizes for performance of your query by batching together rows, so you only have to focus on your processing logic. So this is the promise of UDFs in Athena. You write your function once, you deploy it once, and then anyone in your organization can use the UDF any number of times in their queries. The link I've pasted below highlights a use case and a blog post that shows how you can use a combination of federated queries and UDFs to build a ingestion pipeline. Here's a code snippet on how to invoke a UDF. So the bottom half of the snippet shows how you can define your UDF. The top half shows how you can invoke your UDF in SQL queries. And as you can see, UDFs are simple to write and even simpler to deploy and invoke. And Athena supports scalar functions as UDFs at this time. So how do UDF capabilities help our personas? Anna, she can now invoke custom code in her queries without having to switch between various multiple applications. Carlos does not need to duplicate data for column level access controls. You can simply write a UDF which scrubs the data from the original data set before providing access to Anna. He can also transform data before ingestion as part of his serverless ETL workflow. So for example, at times before ingestion, Carlos might want to transform a particular string into an enum, and that is really simple to achieve using a UDF. Richard, our engineer, can also invoke custom code in applications. And the best part is he can build and deploy a library of UDF once, and then anyone in the organization can use those UDFs to invoke in their queries any number of times. And Maria, she also can transform data that she needs to use in her model training purposes. So at times, as we know, sometimes to optimize the training performance of the model, she needs to transform certain strings into a data type like integer, and that is really easy to accomplish using UDFs. Additionally, she can also apply pre or post processing logic to her result set. The next feature I want to introduce to you is machine learning capabilities in Athena. So if you've been paying attention to Andy Jassy's keynote over the last couple of years, you know that AWS has a mission to democratize machine learning. And this feature helps us to do that. So why do you need ML capabilities in Athena? Our customer conversations have revealed that when you consider number of employees as a dimension, then the number of employees who are proficient in SQL far exceed the number of employees who are proficient in ML-specific technologies. Similarly, the number of employees who are proficient in SQL far outnumber the number of employees who are proficient in a programming language such as Python or Java or C# or any other language. And which is why we believe that the ability to run and invoke machine learning inference using SQL queries is a huge advantage. So using this feature, you can now invoke your machine learning models and use them for inference in your SQL queries. So you can deploy your ML model once on Amazon SageMaker. And again, anyone in your organization can use the model any number of times to run inference. And if you combine Athena's federated query with this feature, then you can run inference on data that is in any data source, regardless of whether that data source supports inherent analysis or inference or not. You don't have any additional need to build applications specifically to run inference, and there is no additional setup required to use this particular feature. This could be a workflow when you want to use Athena to train your ML model. So you can run a federated query to select data from any data source. You can then transform your data set as required, and then you can use this data set to train your ML model and deploy it on Amazon SageMaker. And to use Athena to run inference, your model is already by now on SageMaker. You can write a UDF to pre or post process your data, and then anyone in your organization can run ML inference using data from any data source. I've listed some sample ML use cases here. So for example, our scientist Maria can now help us to predict whether or not a proposed new video game would be a hit. Anna can let us know whether there's any revenue anomalies in transactions or if there's any particular transaction that flags out as fraudulent. And the link to the blog below highlights how you can use Athena in your training workflows and also in your inference workflows. So here's a sample query to invoke inference. The top third shows you how you can invoke inference using SageMaker in your SQL query. The middle third shows you how you can invoke a UDF. And then the select statement shows you how you can use a combination of ML inference and UDF invocation in the same SQL query for your analysis. So how do Athena's ML capabilities help our personas? Anna can now easily run inference on data from any data source, and she can now incorporate additional ML inference capabilities and enrich her dashboards and reports that she populates. Carlos does not need to duplicate data into multiple formats simply to enable ML-specific use cases. And he also does not need to build and maintain an extra application only to enable other analysts in the organization to run inference. Richard can invoke ML capabilities in SaaS applications without requiring to learn new technologies and without requiring to understand and learn new data access paradigms. Maria is no longer an inference bottleneck for the organization because anyone can now use SQL queries to run inference. And she can now switch her focus back to creating and training and deploying the best and the most accurate ML model possible. The next feature I want to introduce to you is Athena's integration with lake formation. As this particular diagram shows, creating and maintaining a data lake is certainly a non-trivial task. You first have to set up your storage, then you have to clean, prepare, and catalog your data, then you specify access control policies, and then you open the data up for analysis. You can see from the right side of the page that you can use Athena to make your data available for analysis. We've considered how you can use Athena's federated query, UDFs, create table as select and insert into to move your data over and to catalog and clean and prepare your data for analysis. And in this section, we'll see how lake formation integration can help you to specify and configure access control policies for everyone in your organization. So how does our lake formation integration help? Before this feature, if Carlos has to provide access to Anna to run a few queries, he has to manage access control in 3 separate services. The first is in Athena to allow Anna to run analysis or run her queries. The second is in the glue catalog to enable her to retrieve the partitions in the table and the metadata information. And the third is S3 where the underlying data actually lives. With lake formation integration, Carlos can achieve all of this centrally using lake formation. Lake formation also allows for fine-grained access control to the column level. Carlos can simply go to the lake formation console or use lake formation APIs to specify column level access protocols. And similarly, Carlos does not need to go to 3 or 4 different services simply to answer auditing and monitoring questions such as who accessed this data, under what, with what permissions, with what roles, and what time, and so on and so forth. Using lake formation APIs or console, he can easily determine auditing and monitoring information in real time. This is how a Athena user request workflow would look like. Carlos first goes ahead and sets up user access protocols and permission levels in lake formation. And then when Anna's request comes into Athena, Athena will request temporary credentials to the lake from lake formation and then use those credentials to retrieve only the data that Anna has access to. This screenshot shows you how analyst 1, who's represented by Anna, is granted access to all of the columns of a particular table, and analyst 2, represented by Maria, is granted access only to the jurisdiction name column. When both of these analysts run their SQL queries, which is a simple select star to this table, as expected, Anna is able to retrieve all of these columns, whereas Maria is only able to retrieve the jurisdiction name column. And I have more features to talk about, but I also want to be mindful of the time because I know you guys are chomping at the bit to see the demo. But very quickly, some of the new notable features are we have added advanced geospatial functions. These are also available in preview, and steps to onboard to the preview are listed at the bottom. We've released Athena workgroups earlier in this year that you can use to isolate your workloads and use workgroups to also specify cost guardrails. We've added support for insert into, added support for the Okta IDP, and also updated our JDBC, ODBC drivers multiple times throughout the year. So the key point that we would want you to take away is how do organizations benefit when you use Athena? So your teams can continue to choose the best fit for purpose database strategy, and Athena does not bind you to any or only proprietary formats. You can use any metadata store. You can have your data in any format, put it in any data source, and use any IDP you want. If we don't support it today, give us that feedback, and we want to support it tomorrow. We're very confident that we will be able to improve the velocity of your analytics and ETL when you use Athena. With this, I'll have Anthony over to the stage to run you through the demo.
Thanks, Yannick. As Yannick mentioned, my name is Anthony Virtuoso. I'm a principal engineer with Athena. And today what I'm going to do is I'm going to walk you through how easy it can be to get started with Athena Query Federation. And to do that, we're going to do two things. First, we're going to deploy a ready-made connector and then use it in a federated query in Athena. And by ready-made connector, I mean one that the Athena team has written and then published for you to use in AWS serverless app repo. The second thing we'll do is we'll actually write a new connector to a custom data source with a proprietary file format live today. We'll also include a couple UDFs in that connector, and then we'll also use those in a federated query from Athena. So up on the screen right now, I actually have our GitHub repo. Everything that I'm going to show you, and in fact, pretty much everything related to federated queries in Athena is open source and available on this repository. There's a pretty detailed tutorial as well that I'll point out in this Athena-example folder. A lot of what I'm going to show you is essentially walking through this tutorial. Excuse me. So to get started, I'm going to navigate over to AWS serverless app repo, and I'm going to search for Amazon Athena Federation. Amazon Athena Federation is the name of the author that the Athena team uses when it publishes connectors to serverless app repo. And you can see that it pulled up about 10 or so connectors here, and each of those has the AWS verified author badge. When you see that badge, you can rest assured that the code you're about to deploy has been authored and is maintained by the Athena team. So I'm going to scroll down and go to our Athena CloudWatch connector, because that's the one we're going to deploy right now and then use in a query. And when you click on the connector, you get some information about it, including down to the very nitty-gritty details of what deploying this connector will do in the form of a CloudFormation template. Further down, you can see what permissions this connector needs. In the case of the CloudWatch one, it needs access to S3 for potentially spilling large responses, and it also needs the ability to read from CloudFormation, from CloudWatch logs. And then if you scroll down more, you'll get a detailed README of what all the configuration options are, how you can use this connector, what tables it supports, and so on. On the right-hand side, we get some of the configuration information that we can provide for this connector. The first thing that we need to fill in is an S3 bucket that the connector can use for spill. So I've already created one. I'll go ahead and type that in. The second thing that we need to provide is what is the name of this source? What do we want to use in our SQL queries? What do we want the Lambda function to be called? And so I'll just simply call this CloudWatch to make it easy. For any data that might spill to S3, we encrypt it by default. You can optionally use KMS for key management of that spill, but by default, we will use a local source of randomness from your Lambda function. So I'm going to leave that as a default. I can also control how much memory and how much Lambda runtime the function is allowed to use. And then lastly, I can set a spill prefix in that S3 bucket to make it easier for you to set up S3 lifecycle policies to delete that data after the query finishes. I'm going to check this box that gives the serverless app repo permission to create the scoped down IAM role that this connector will need. And then if I scroll way to the bottom, I can deploy that connector. And so essentially what's going to be happening right now while serverless app repo prepares to deploy this connector is it's taking that CloudFormation template that I showed you before. It's filling in the variables that I just provided for my spill bucket and the name I want to give the Lambda function. And the first thing it's going to do is it's going to go and create those scope down roles, which is what it's doing right now. And then once it's created the scope down roles, it'll go ahead and deploy the Lambda function itself. That entire process usually takes about a minute or two, depending on the complexity of that, the IAM role that the connector needs. So while that's deploying, I'll just scroll down here and show you a little bit more information. So with each of those connectors that we've published, we include a pretty detailed README. In the case of this particular connector, it also gives us an example query that we can run just to kind of quickly get started. It also gives us all the instructions we would need if we wanted to build this connector from scratch, maybe because we want to modify it for our own needs, or just because we're curious in how it specifically works. So if I scroll back to the top, I can see that the deployment succeeded. Now I'm going to switch over to my Athena console, and I'm going to make sure that I'm running my Athena queries in a special workgroup called Amazon Athena Preview Functionality. So this is going to be the way that you'll tell Athena that you want your query to use preview capabilities. We wanted to make sure that it was very easy for you to opt in, but not to accidentally send your production workloads through that preview capability. So I'm already in that workgroup. I'm going to switch back to our query editor. And I've already copy-pasted that query from before, except I've made 2 changes to it. I've substituted in the name of my source everywhere where it had previously said Lambda function name. So what this query is going to do is it's going to go and grab all the details of the log lines that exist inside of our CloudWatch connector for a log group called AWS Lambda CloudWatch. This is actually the log group for the Lambda function that runs the connector. And then it's actually going to query a table called all log streams. And this table is essentially a view over all the log streams that are contained in that log group. I'm going to go and run that query, and this will probably take about 10 or 15 seconds to run. And what's happening right now is essentially Athena is calling that Lambda function during query planning to say, what are all the different log streams that I'm going to need to read? And then Athena will call that Lambda function for each log stream and actually affect the read. And you can see I got back my log lines down here. And so the reason I'm showing you this is just to give you an idea of how quickly you can get started with federated queries. Now, obviously, depending on the source you're connecting to, you're going to need to provide more or less configuration information. For example, if you're connecting to an RDS instance for federation, you're going to need to provide VPC details so that that Lambda function will have network connectivity to your RDS instance. So now that we've seen how to deploy a ready-made connector, let's take a look at what it takes to write a connector from scratch. And if you remember, I mentioned before that all this stuff is available on the GitHub repo. I want to make sure I call that out again, because we're going to go through some code right now. And I don't want you to think that you have to absorb all of it in this moment. My goal is really to show you how simple it can be to integrate with a custom source, or to take one of our existing connectors and modify it, for your own purposes in case the generic one we've made doesn't quite fit your need. So in order to do that, I'm going to just switch over to an editor where I've checked out a copy of this GitHub repository. And there are essentially 3 files that we're going to need to modify in order to create our custom connector. So we provide this example project as essentially a way for you to get started. It has all the boilerplate taken care of for you, and then it has comments in each of the important functions where you should go and add your business logic or add your logic for connecting to your proprietary source. So the first file that we're going to be modifying is called example metadata handler. And as the name implies, the functions in this file provide Athena with metadata about our source. So during query planning time, Athena is going to call the functions that we're about to modify. The first function that we're going to implement is called doListSchemaNames. And essentially, Athena will call this function to get the list of schemas or databases that our custom source supports. Most likely, Athena would call this if somebody did a show databases SQL statement. So I'm just going to uncomment the code that's already there in the example. And in this particular case, all we're doing is returning a hard-coded list of schemas, in this case, schema 1. The second function we need to implement is very similar to that previous one. It's called doListTableNames. And essentially, this is how Athena will get the list of tables in a particular schema or database. And again, we're just returning a hard-coded, in this case, fully qualified table name, where we're saying whatever the schema you requested is, it always has a table called table 1. Again, a somewhat contrived example, but I'm just trying to illustrate how simple some of these functions are. The next function is a little bit more involved. It's called doGetTable. And this is essentially the function that Athena will call when it wants to get the detail of our table. What are the columns that it has? What are the types? Is it partitioned? If so, what columns is it partitioned on? And so the first thing that we do in this function, in this particular example, is we define our partition columns. And here we're saying that this table, table 1, is partitioned on year, month, day. And then just below that, this is our first time that we're going to be interacting with Apache Arrow as part of this connector. If you recall earlier, Janek mentioned that a lot of this protocol is based on Apache Arrow in order to have a very easy interchange format. So in this particular case, what we're doing is we're building an Apache Arrow schema object where we're going to define all the columns that are in our table. And the first 3 columns we define are integer fields. In this case, they're year, month, and day, and they happen to correspond to our partition columns. The next field is a string field called account ID, followed by another string field called encrypted payload. This is actually going to be a little bit of an interesting column in our example because the sample data that we're going to upload to S3 and then query is actually going to have this column AES encrypted. So we won't be able to read it without using our UDF that we'll write later. We then add a complex column of type struct, and we say that that struct column called transaction has 2 child columns, an ID column and a completed column. And that's essentially the core of the schema of our table. The next things that we end up adding are pieces of metadata. And for the most part, Athena doesn't really understand metadata on your table. You can think of these as table properties. The only time Athena really understands them is if it sees a piece of metadata whose name matches the name of a column, Athena will assume that's the documentation of the column. And so if somebody does a described table, Athena will take that value and actually show it in the result of the described table as documentation for your user. That takes care of our getTable function. The next function we need to implement is called getPartitions. And this is our first opportunity to control how Athena parallelizes reading our table. In this particular case, we're just looping over our partition columns, generating some random values. So we're looping over year, month, and day, and essentially just generating some preset number of partitions. But the interesting part of this function comes in when we go to return that data to Athena. So essentially, what we get to do when Athena calls this function is that it's going to provide us the query predicate. And so we'll be able to apply partition pruning to remove the partitions that Athena doesn't need to read because they won't contain any relevant data. And the way we do that is by using this block object. When we do block.setValue, under the hood, the SDK is actually writing that value. Excuse me. The SDK is actually writing that value into an Apache Arrow response object for us. And it'll return a Boolean that tells us whether or not that value satisfied the query's constraints. We collect all those Booleans to decide if this particular partition is one that Athena needs to read, and then we return either a 1 or a 0 to tell Athena if we wrote a valid row or not. And then the last function that we need to implement in our metadata handler is called getSplits. This is our second opportunity to tell Athena how it can parallelize reading our table. And essentially, as the name implies, we're going to tell Athena how it can split up the reads for that particular partition. So similar to the table properties that I mentioned before, Athena doesn't really know what a split is. For the most part, a split is there for us, because Athena will call us for each split and say, hey, can you go read this for me? But there are a couple fields on a split that Athena does understand. The first one is the spill location. And here I'm using this function, makeSpillLocation, provided by the SDK to create a spill location. And a spill location is essentially a path in S3 that is unique per split. So that if the data represented by that split is too large to come back in the Lambda response, the Lambda function will spill that to S3, and Athena will go get it from there. The thing that's somewhat interesting about this is that because we tell Athena the spill location ahead of time, Athena doesn't need to wait for our Lambda function to complete before it can go get that data. Athena will actually start to prefetch and watch that S3 location. As soon as data arrives, it'll process it. The reason why that's important is because imagine if your Lambda function was going to read 10 gigs of data. We don't want to essentially have Athena waiting around for your function to read 10 gigs of data, write it to S3, and only then will Athena begin to process it. Instead, we want to pipeline those reads and writes, and having this spill location lets us do that because Athena will begin to read even before you finish writing. The second piece of information on the split that Athena will understand is an encryption key. And so Athena will use this encryption key to decrypt any data that gets spilled. And in this particular example, I'm also using a utility from the SDK called makeEncryptionKey that under the hood will either use KMS or a local source of randomness to generate the encryption key for me, depending on how I've configured my connector. The next couple pieces of information that we put on our split are year, month, and day. And again, these are for us. Athena will not understand what these things mean, but Athena does know that it's important for it to call our Lambda function for each split. And you'll see how we'll end up using the year, month, and day properties on this particular split in the next section. And so there you have it. In, I think, 5 functions, we've just implemented all the metadata required for Athena to be able to plan a federated query. The next thing we're going to do is we're going to move to this file called example record handler. And here we're actually going to implement only a single function, and that's going to be the function that Athena will call when it wants to actually read a split. So for each partition that we gave Athena, Athena called us to generate splits. And then for each of those splits, Athena will call us to go and read the data associated with the split. So let's take a look at what we need to do to read a split. So the first thing that we do is we need to figure out what the split is asking us to do. And so in our particular case, we're going to grab those 3 properties that we set on the split, the year, the month, and the day. And that's going to tell us where we need to go do our read. For this particular example, we're going to be uploading our sample data to a specific bucket in S3. So with this piece of code, we're going to go and grab a Lambda environment variable called data_bucket, that's going to essentially just be the configuration for where our data is stored in S3. Again, this is a bit contrived. In a real-world situation, you would be reaching out to the actual data store and figuring out where that data lives. It's unlikely that you would be hard-coding a single bucket or single location. And just below that, we can actually see what this example ends up doing with that year, month, and day information. It's essentially creating a path in S3 to a specific file that represents that partition or split. It then opens that file, and we'll see later on it'll loop over that CSV line by line and translate that into Apache Arrow before sending it back to Athena. The next interesting thing that we end up doing in this file is we actually have to set up that translation. How do we go from a CSV to Apache Arrow? And to do that, we end up using a utility from our SDK that ends up hiding a lot of the nuance of Apache Arrow. And the thing I want to call out here is that even though I'm going to walk you through a utility that essentially abstracts a lot of Apache Arrow, you can at any moment choose to just drop down into a more power user mode and interact with Apache Arrow directly. And in fact, if you do choose to do that, you can often achieve better performance than using some of these abstractions. But I can assure you that these abstractions will minimize the amount of code you may need to write to do your integration. So you kind of have to balance that performance with maintainability there. So essentially what this generated row writer does is it gives us the opportunity to provide it with the pieces of code that are required for extracting and translating each of the columns in our source or in the table that we're reading. And then at the end, we will use that generated row writer to actually compile some or to do some on-the-fly pseudo code generation so that when it's actually translating every row from the source to the destination, it's not having to do a lot of metadata lookups or see is this column an integer or a string, and then what's the coercion for that. So we're doing a little bit of code gen here to improve that performance. So let's take a look at just one of these extractors, since for the very simple columns, they're pretty basic. So for the year column, what we're essentially saying is that we're going to take the first column out of the CSV, we're going to parse it into an integer, and then we're returning it. There's not a whole lot there. These are very simple columns. But if we move down a bit, it gets a little bit more interesting. So let's take a look at the extractor for that account ID. So it turns out that in this particular example, account ID is a sensitive column to the business. And they don't actually want to grant access to the entire thing. Instead, they only want to grant access to the last 4 characters. So what this particular extractor is doing is it's grabbing the account ID out of the CSV. It's then checking the length of that value, and then only grabbing the last 4 and returning the last 4 characters of it. So in this way, you're essentially affecting masking of that column. The last column that we need to write an extractor for is a complex value. We had defined a struct column called transaction ID earlier that had 2 child columns, an ID and a field called completed, which was a Boolean that told us whether or not the transaction had completed. And the way we do that here is we essentially create a map that corresponds to the fields in our struct, and we use a utility from the SDK called blockutils to set that complex value. Now, the thing that's different here from some of the other examples we looked at is that for complex values, our SDK doesn't yet support predicate pushdown. So at the bottom, we're returning true to say it always passes the filter, and we'll rely on Athena to do the filtering of any of the complex types. Whereas with those other columns that we wrote extractors for, like year, month, and day, the SDK will underneath automatically take care of applying any of the query predicates so that it will reduce the amount of data that gets sent to Athena. And then the last thing we do is we call build on our generated row writer to do that code generation. And at that point, we've got a translator that can be used as we loop over each of the lines in the CSV. And then we end up using this spiller utility, or I should say a block spiller utility, to actually write the rows back to Athena. Under the hood, this block spiller will automatically take care of chunking up our response, encrypting it, and potentially spilling it to S3 if that response gets too large. And so there you have it. We're now done writing our connector. The next file we're going to look at will actually contain 2 UDFs that we'll use in our example query. Okay, so our first UDF is called extract transaction ID. And it's a fairly simple function. All we're going to use it for is to extract the ID field from our complex transaction type. And so the first thing that the code here does is it just checks to see, is the input valid? Is it non-null? Does it actually contain an ID field? If it doesn't satisfy those, it returns a -1. The reason for returning a -1 in this example, instead of just throwing an error or something, is because I didn't want to fail my query. right? You have complete control over what you want to do when you encounter data that's maybe not perfect, whether that's returning a default value or trying to recover it some other way. Assuming that field is present, we essentially get it from the map that we're provided, and then we cast it to an integer and return it. And that's essentially it for our first UDF. Our second UDF is a little bit more interesting. It's called decrypt. And what we do inside of this function is we're going to attempt to decrypt the column or value that we're provided. And the first thing that happens there is we need to grab our encryption key. In this particular example, if you end up checking it out of our GitHub repository, there's just a hard-coded key in there. But in reality, you would probably reach out to something like KMS or AWS Secrets Manager or wherever you hold your encryption keys to retrieve the key that you can use to decrypt that column. Once we have the key, we call our symmetric decrypt function, and we provide it the value that we want to decrypt as well as the key, and then it returns for us the clear text version of that column. Same as in the previous function, if we encounter any errors, we're just returning a default value, in this case null. Otherwise, we're returning our decrypted value. And we're done with our two UDFs. So the next thing that we need to do is we need to compile, test, and then deploy this connector and UDF suite. And in order to do that, our SDK comes with a helpful utility called publish. And essentially what publish does is I give it the name of the S3 bucket where it can upload the compiled connector to as a handoff to serverless app repository. I then also give it the name of the module in the Maven project that I want to compile and turn into a connector. And then I tell it what region I want it to deploy to. I'll go ahead and hit enter here, and it'll give you a more complete list of what it's going to do. But essentially, once this command finishes, it will have tested and validated my connector and UDFs. It will have published it to serverless app repo as a private application just for me. And then later on, I can choose to make that public or share it with other people in my organization. So I'll go ahead and hit yes. This will probably take a minute or so to actually compile and upload. And so it just finished running through its unit tests. It's now turning it into a bundle that can be deployed to serverless app repo and uploading it. OK. And so at this point, it now has the application available for us in serverless app repo. So I'll go ahead and switch back to my browser. And if I navigate to serverless app repo and go to private applications, you can now see our example connector here. So I'll go ahead and click on that, and we'll deploy it, and then we'll use it. So I'm going to give it a name. In this case, I'm just going to call it example. And that corresponds to the name of the Lambda function, as well as the name that I will use in my query to access that source. It's asking me for the bucket where I uploaded my sample data. I've done that before, so I'll go ahead and type that in. It's also asking me for a bucket where it can optionally spill data to, and I'll fill that in. Everything else I can leave as default, and I'll go ahead and click deploy. So same as before, this is going to go and create the IAM roles that this connector needs. It's then going to go and create the Lambda function and deploy the code that we just wrote together. So we'll give that a moment to do its thing. Actually, while it's doing that, I'll show you guys the test query that we're going to run. OK, so here we have the test query that we'll execute. The first thing this test query does is it defines our first UDF, the extract transaction ID. And we essentially just need to define what its parameters and return type are. The reason we do that is because when Athena goes to run the federated query and calls the Lambda function is going to match the signature of the UDF as it appeared in the SQL with the signature of any of those Java functions that we wrote in that file. And if it finds a match, that's essentially how the pairing of UDF happens. And we essentially tell Athena that this UDF is of type Lambda invoke, and it's hosted on a Lambda function called example. And then we do the same thing for our decrypt UDF. And then we're selecting year, month, and day, as well as the account ID. We then select our encrypted payload column, but we use our decrypt UDF to decrypt it so that we'll be able to read it, before then calling the extract transaction ID UDF on the transaction column so that we can just get back that ID field. And then we're doing a from Lambda : example. And this is how we're telling Athena that this particular table is a federated table and is hosted on a Lambda function called example. And then I'm just scoping down my query to be a single partition, 2017, November, and the 1st. So let's see if it finished deploying our connector. And yep, it looks like I finished deploying, so I'll go ahead and run this query. It should take about 10 seconds or so. And again, what Athena is doing under the hood here is it's calling our Lambda function during query planning to get the details of the table. It's then calling the Lambda function to do the read, and then it's calling the Lambda function again with batches of rows to execute the UDFs. And we can see we got our data back. So we have our year, month, and day column. Our account ID column has been masked down to just 4 fields. Our decrypted payload has been, our encrypted payload has been decrypted, and now we can read it. We see that it says secret and dash the transaction ID. And lastly, we've successfully extracted the transaction ID from our transaction field. So there you have it. I think in about 20, 25 minutes or so, we deployed a connector that was ready made. We wrote a connector from scratch, and we wrote a couple UDFs from scratch. I want to thank you guys for joining us today. We're pretty excited to see how you guys use this new functionality. I think Janik and I will be hanging out for a few minutes after for any questions, although we ask that we kind of do that outside so that they can prepare the room for the next talk. Thanks, everyone.